Imagine a place in space, a region unlike any other we know, where gravity is so incredibly strong, a force so immense that not even light, the fastest thing in the universe, can escape its grasp. Nothing can break free. This is a black hole, a cosmic phenomenon that continues to captivate and challenge our understanding. It's a region where matter is packed into an incredibly tiny space, compressed to an unimaginable density, creating a gravitational pull so intense that it dominates everything around it. It warps space and time itself, bending the fabric of reality. Black holes aren't empty holes or sci-fi tunnels leading to other dimensions. They are far more complex and fascinating. They're often the collapsed cores of massive stars that have reached the end of their life cycle, or the supermassive giants lurking at the centers of most, if not all, galaxies, exerting tremendous influence on their surroundings. Our own Milky Way galaxy has one Sagittarius A star, a supermassive black hole, with a mass approximately 4 million times that of our Sun, a truly staggering figure. We can't see black holes directly with our telescopes as they emit no light, but we can detect their presence indirectly by carefully observing how they affect the motion of nearby stars and the behavior of surrounding gas clouds. We see stars orbiting around what appears to be an invisible object, moving at incredible speeds, or observe gas glowing intensely in X-rays as it superheated and pulled inexorably towards the event horizon. Even Einstein himself, the father of general relativity, initially doubted their existence. But as mounting evidence accumulated over decades, and we even managed to capture the first ever images of their shadows, the dark silhouette against the glowing accretion disk have definitively confirmed that they are indeed real and present throughout the universe. Black holes are now recognized as fundamental parts of the universe, playing a crucial role in the cosmic architecture, shaping the evolution of galaxies, and constantly challenging our current understanding of the fundamental laws of physics. They're invisible, mysterious, and incredibly powerful, cosmic enigmas that continue to beckon us, urging us to explore the deepest mysteries of the cosmos. Their very existence pushes the boundaries of what we know about the cosmos, forcing us to rethink our understanding of the universe. They're not just a theoretical concept confined to textbooks, they're a fascinating and undeniable reality shaping the universe around us. And they're undoubtedly one of the universe's greatest and most compelling mysteries, holding secrets that we are only beginning to unravel. Black holes fascinate us because they push physics to its limits where gravity, space, and time break down. They're natural laboratories for testing our biggest ideas about the universe. Since nothing escapes a black hole, we can only study their effects from the outside, piecing together clues like cosmic detectives. This challenge drives scientists to use powerful telescopes and simulations to unlock their secrets. Black holes force us to ask profound questions. What happens to matter that falls in? Is information lost forever? Could they be gateways to other universes? These aren't just sci-fi ideas, they're real scientific mysteries. Black holes inspire awe and wonder, reminding us how much we have yet to learn. They're the ultimate cosmic puzzle, fueling our curiosity to explore the unknown. Picture yourself as an astronaut approaching a black hole. From a safe distance, it's just a dark circle warping the starlight behind it, a cosmic lens. As you get closer, gravity intensifies, and the view outside twists into glowing rings and distorted stars. Move closer still, and the black hole's pull becomes overwhelming. If you drift feet first, gravity tugs harder on your feet than your head, a tidal force that starts to stretch you. The universe outside looks like a funhouse mirror, and your journey becomes a battle against gravity itself. The closer you get, the more you're pulled apart. This is the beginning of a process scientists call spaghettification. The adventure turns from curiosity to a one-way trip into the most extreme environment in the universe. The real challenge is just beginning. As you approach the black hole, the gravitational forces begin to intensify, subtly at first, then with increasing urgency. You're drawn closer, the point of no return looming ever larger in your view. You're about to reach the event horizon. This is the event horizon, the point of no return, a boundary defined by gravity itself. It's the threshold beyond which nothing, not even light, can escape the black hole's relentless pull. It's not a physical wall, something you could touch or bump into, but rather a boundary in space-time. It's a region where escape becomes utterly impossible, even for light, the fastest thing in the universe. Photons themselves are trapped, circling endlessly, unable to break free. Cross it, and you're irrevocably lost to the observable universe forever. There is no turning back, no escape, only a one-way journey into the unknown. From your perspective, as you cross this boundary, nothing particularly dramatic seems to happen at first. You simply float onward, seemingly unaffected, continuing your trajectory as if nothing has changed. But to an observer far, far away, watching you approach with a powerful telescope, you appear to slow down as if time itself is bending around you. Freeze, your movements becoming more and more sluggish, and fade at the edge of the event horizon, your light growing dimmer and dimmer, thanks to the incredibly warped space and time around the black hole. Time for you, from their perspective, slows to a crawl compared to the outside world, almost grinding to a halt. Your image lingers, becoming increasingly red-shifted and dim as the light waves stretch out. You appear to hover, never quite crossing the line, forever frozen at the edge of oblivion. This strange and counterintuitive effect is a direct prediction of Einstein's theory of general relativity. It highlights the bizarre nature of black holes, two drastically different realities depending on where you are observing from. Once inside the event horizon, you're completely cut off from the rest of the universe, unable to send any information back. Your fate is sealed, inexorably pulled towards the singularity by the immense grip of gravity. The event horizon, therefore, represents the ultimate cosmic boundary, a point of no return in the grand theater of the universe. As we venture closer to a black hole, passing the point of no return, we encounter the event horizon. Inside this boundary, tidal forces become extreme, a phenomenon we call spaghettification. It's a rather descriptive term, isn't it? Imagine the gravitational pull acting unevenly on your body. Gravity pulls much harder on your feet, which are closer to the black hole, than on your head. This difference in gravitational force results in a dramatic stretching effect, elongating you into a long, thin strand, much like spaghetti. Think of a rubber band stretched to its absolute limit, pulled so hard that it snaps under the immense pressure. In a similar, albeit far more violent fashion, black holes do this to anything, stars, planets, even unfortunate astronauts, that gets too close. The size of the black hole plays a crucial role in how this process unfolds. For smaller stellar mass black holes, this stretching, this cosmic shredding, happens well before you even cross the event horizon, meaning you'd be torn apart before reaching the point of no return. However, the story changes with supermassive black holes, the behemoths residing at the centers of galaxies. With these giants, you might cross the event horizon relatively unscathed, only to be stretched and ultimately destroyed as you approach the singularity, the black hole's center. And this isn't just a theoretical exercise, a dark prediction from the equations of relativity. We've actually observed stars being violently torn apart by black holes, their destruction lighting up the cosmos in spectacular, dramatic flares of energy. Astronomers have a name for these events, tidal disruption events, and they serve as compelling proof that spaghettification is not just a theory, but a real, observable phenomenon in our universe. It's a stark and powerful demonstration of the immense might of gravity, showcasing its ability to warp and distort even the most resilient objects. Black holes are not merely cosmic vacuum cleaners, passively swallowing matter. They actively shred, tear, and reshape the very fabric of the universe around them, leaving no trace of what once was. Spaghettification, therefore, represents the ultimate, unavoidable fate for anything or anyone that dares to venture too close to these enigmatic cosmic giants. What happens at the center of a black hole? Our best theory says everything is crushed into a single, infinitely dense point, a singularity. Here, space and time break down, and our laws of physics stop working. This infinity signals that our understanding is incomplete. Some scientists propose alternatives. Maybe matter transforms into something exotic, or perhaps the center is a wormhole to another universe. But there's no evidence. These ideas remain speculation. The event horizon traps all information, making the center a permanent mystery. We can only theorize, never observe. The heart of a black hole is the ultimate unknown. Our journey ends in mystery. Black holes are the universe's locked rooms. We study their effects, but the inside remains hidden. New telescopes and gravitational wave detectors are giving us fresh clues, but the core questions remain. Do black holes destroy information, or is it preserved in ways we don't yet understand? Solving these puzzles could revolutionize physics. Black holes remind us how much we have to learn and inspire us to keep exploring. They're symbols of the unknown, driving curiosity and discovery. As long as black holes exist, there will always be new frontiers to explore.